Hello, SolarLune here, and here is another 2D Blender game engine tutorial. Someone asked me how to do some more complex things, like actually implement the sprite into a game, into a gameplay. So that's what I'm going to do. Today we'll be basically making our character here, our 2D character, our plane, animate when he moves around, turn around, different things like that. So this isn't quite the same sprite as the previous tutorial. As you can see, it's a little different. I lost the previous sprite, I think, so this guy I pixeled up not too long ago. So here I'm going to press Control up here. Is his sprite sheet, and this is the, for some reason, well, not for some reason, this is the transparent color pixels. GIMP saves these colors when you save it, but you if it's transparent, obviously you can't see those colors. So that's our character here. He's got 2 frames of walking with a standing in the middle, and 4 standing animation frames. Okay, so going back, we've already defined our sprites as before, as these planes. You probably see that there's a lot more of a margin around the characters. They're 16 by 16, or the sprites. They're 16 by 16 like before, but I have a little margin because if you have too close, if the sides of the sprites touch the sides of the sprites for the next frame, sometimes you'll get a little seam where you can see the colors from the sprite frame kind of spilling over. By having a padding area, that makes it easier, or that makes it impossible for those things to show up, for those seam colors to appear. So it's just nice and crisp. Now it's a lot of padding. It could just be like a pixel really, but it's basically almost 16 pixels because I need to have a power of 2 image for Blender to interpolate the textures without any blurring. Because if you have a non-power of 2 image, it's going to be blurry. So a power of 2 image is 64 by 64, 128 by 128, 256, 512. I don't think it has to be exact, like even. Like you can have 64 by 128 or 512 by 32, but you do need to have a power of 2 sized image. Now the method I'm using here is bitmaps off to have the textures be as sharp as possible. You could also use just large textures, and that would be good as well. Something that you need to be aware of, or probably should be aware of, is that when you use multi-texture mode, for some reason I can't pass no bitmaps. I can't pass that argument to the executable. So bitmaps are always on regardless of whether you want them or not. So if you don't want bitmaps, you can use single texture mode or GLSL mode when you use runtimes. But it seems like multi-texture mode doesn't work with command line arguments, which is the method that you would use to turn off bitmaps and run the game in an executable. I submitted a bug report to the bug tracker, so hopefully it'll get fixed soon. But in the meantime, you can use either single texture mode or GLSL mode. So you can choose between kind of like PlayStation 1 and PlayStation 3 kind of a setup. Anyway, or I guess Game Boy, if you really, if you do it right, it could be some really retro styled graphics. Alright, so anyway, that aside, yeah, so this is our sprites. We have defined them as, we have defined their names rather, as the individual sprite frame, sprite frames according to our previous tutorial. So we have 4 frames of standing, 3 frames of walking, and they're all in a resources group. And in the game scene, we have in a hidden layer, the resources group as an instance. So this basically adds in all of those individual frames. So it's easy to add in all your added objects, put all your added objects in your resources scene, and then just pop them all in. And this could be also useful if you wanted to have like a moddable game. You could either make the editor and different things like that yourself, or you could tell people download Blender and open an external blend file that contains all of your resources, all your sprites, all your everything like that, and then go ahead and have fun with it. Add add sprites, change sprites, whatever. if you don't pack your textures, you can even change it that way. And say, if you want to mod the graphics, just go and find player.png and change his colors, change his whatever, change everything. All right, so anyway, yeah, so we have everything, all the resources, all the frames in the hidden layer, and our game, our simple character with a collision box. The character plane is here. The size pretty much exactly in line with the collision box. Something that you might want to take note of, I'm pressing N here to open this, is that, let's see. Oh yeah, I have basically just a little side note. These little grid spaces in the back, I've aligned them to 16 by 16 pixels. 16 by 16, a grid size is 16 by 16 grid lines. One big square like this is made up of 16 by 16 smaller lines, and those basically represent pixels. So for example, I can go ahead and drag this over exactly 1 pixel. So I just wanted to point that out. And you do this by changing the subdivisions number here. As you can see, you might be able to see it, but yeah, the number of smaller grids, the number of, I guess, grid cells in each large grid square is defined by this subdivision amount. So 16 gives you pretty much exact pixel per pixel control in movement, placement, grid snapping, all that stuff. And to snap to grid, make sure you have this little snap button enabled. Alright, so let's see what we have so far. So we see the player here, he's walking. Simple, quick, he's just doing a simple treadmill walk animation. So let's see also the script, of course, the script for our player. So in the player.py file, we have a player function, and you can see this here. We have the player cube, and it's running the player.player function, and it's set to run always. The player sprite here is parented to the player object, so if we move the player around, the sprite follows. If we move the sprite around, the player doesn't move. Alright, so everything's good, he's walking, and if we look at the script, it's pretty much the same as before, except for one thing that I forgot to delete in testing this out. But yeah, it's working pretty well. So we set the sprite animation to a list that consists of the name of the animation and then the individual frames. And then we run the sprites.spriteMesh function with our sprite object as the argument, so that it animates that object. We get the sprite object in the init function with this little list comprehension, which is basically for all objects, for all children of the current object, of the player object, which is just the sprite object. But for all of those children, if it has SPR in a lowercase version of the name, c.name is a string, that's the name of the object, and get the lowercase version of that. If SPR is in there, then we get the first, then basically we make a list of those objects, which is just one. And then we get the first object in that list. And so that's how we get the sprite object. And so we run the animation. So here we define these two functions, the init function and the update function, and we check to see if the init function ran all right. And if so, we run the update function and thereby animate the player. One last thing that I didn't have in the previous version, previous part of this tutorial, is this variable. This gets basically the logic module, Python module, has a keyboard variable that is a pointer to the global keyboard, the keyboard that you have connected to your computer. Oops, my mistake. The keyboard that you have connected to your computer. And so basically this, just like there's also one for a mouse. And so you can get mouse presses, keyboard presses, different things like that. Now the usual method is to get logic.keyboard.events and check to see if a key code is active. Now the difference here with active events is that it runs faster than events. It's like 4 times faster in some cases, I believe, but it's naturally empty, and so you have to check to see if your key is in the events dictionary before you check it. So we'll walk into that in a little bit. So first things first, everything's working well. First thing that we want to do is kind of abstract out this animation code. We don't want to set the animation like this every frame. That could be a little slow, or just a little awkward. So what we're going to do is have a object variable that says which animation we should play. So we'll set this to walk, a string named walk, and then we'll have a dictionary of animations that corresponds our animation names here with the animations we should play and their frame rates. So that's something I didn't cover in the previous tutorial, is how to speed up or slow down your animations. Basically, my Sprites module here has a lot of built-in variables like SPR anim. Basically, if you don't have that already, it will create it, but it will use that to animate your sprite. And so there's another one called SPR FPS that changes how fast the animation should play. So let's go back and create this dictionary. So I don't know if you know, but a dictionary is something like a list, but instead of associating values, data with a numerical index like 0, this list, let's say this is a list. The name of this list is list, like that's the variable name. List 0 is player walk R, list 1 is 0, list 2 is 1, list 3 is 0, list 4 is 2. That's a list. A dictionary is like that, except instead of using a number like 0, 1, 2, we use another data type. So you can use that, for example, to say animation name is this, animation frames are these, and so forth and so on. So I'll show you. Okay, so we're going to create a little dictionary here. We're going to name this walk, like that, create a colon, and then create a list. So anytime we access the walk index of the animdict variable, we will get this list. And so this list will be this. Let's cut that out, put that there. And we're going to be looking at the animation and then how fast it should play. I know that's 6 frames per second already that I want. And then we'll do the same for stand. Now stand is a little longer, so I'm going to run through that in a second. But first, let's go back and make sure that this is working. So we go ahead and check to see basically that we want to set the sprite animation to be the animation dictionary's animation that we define here, that we access with the anim variable. So we say anim equals obj anim dict, or dict, obj anim. So that's our animation. So this anim variable will be basically this. It will be this list here. So we want the animation to be anim 0, and we want this frame rate to be SPR FPS equals anim 1 with brackets. Okay, so that should work. Let's check it out and see if it does. Yeah, he's walking, and slowly. So it's working. Now, the next thing we'll probably want to do, hold on, let me make sure I'm on track here. Yeah, I think that should work. Okay, yeah, everything's good. Now the next thing we want to do is change this out, because we probably don't want this animating in the same function that we're checking for input, doing different things like that. So let's change this from update to animate and create a new update function that calls the animate function. It also could be down here. I would kind of rather it be down here, but sometimes you want it to animate even in a certain little place. So we'll leave it the way it is. So if the initial object initializes and all the variables are set, so it checks to see if the object's initialized, and if it isn't, it initializes everything. And if it is initialized, it returns 1, so that function's done. And then it calls the update function, which calls the animate function. So let's go ahead and make sure it's working well, and it is. Now, the next thing we're going to do is check for input. Okay, so we have a keyboard dictionary here that basically consists or holds our keyboard values, our key codes, as well as our key press, the event status for those key codes. So what we're going to do is we're going to import the events module from the BGE module. And that will basically allow us access to the key code constants, so that we don't have to identify, say, the left key code by 146. That's the key code. We can use a name for it. Okay, so we check to see if a keyboard key is pressed. Now, the last time I did this, I actually just did this and typed it out, but I'm going to make a function for it. So let's type it out first and make sure it works, and if so, we can actually do the rest. So we say if, wait, no, let me back up. Let me make something else. Something else to make this easier would be key bindings. And basically a key binding is a way to just refer to a key code by a name. Because even though events allows us to refer to a key code number by a name, it's still a rather long name. So what we're going to do is say left is events.left arrow key, and make that a colon comma at the end. And we're going to make a few of those. Left, right, jump, and action. We'll probably not, well, I think I'm only going to get into left and right now, but we'll just set this up for next time. Left, right, we have a X for jump and C for action. Okay, now we say if obj kb left in keyboard and keyboard obj kb left equals logic.kx input active print move left. Alright, so that's kind of long, but we just check to see if the key code is in the keyboard dictionary, and if so, and it's active, if it's being pressed, then we move left. So well, actually, let me also do something else. Let's see this in action. We're going to print out keyboard so we can see the keyboard dictionary while before we actually do anything. So I'm going to move the console window over. Let me see. I need the console window. Here we go. And so we're going to see this as it goes. So we're going to play it and then look at the console. So you can see, I'm not sure if you'll be able to see this. Yeah, I don't think that you'll be able to see this because Blender kind of steals input. Alright, well, unfortunately I can't show this on screen. Oh well. Alright, so, in any case, you see here, this value, 125, I believe that's the tab key. And you see that 125 is the index, that's the key code of the tab key, and then 1, 2, and then 3 at the bottom are the event status of the key code. 1 means just pressed, 2 means being held down, and 3 means let go. Now, we could use numbers, but Blender gives us a keyboard constant that we can use, and that is what you see here at logic.kx input active. That's 1 or 2, because 3 is just let go. So logic.kx input active is holding down the key. Alright, now like I said, I was going to do this whole thing like this, but I'm going to kind of abstract this out to a function, and you can see why I do so when we do the right key too. So we'll make this the key down function, and we'll read a key code value. We'll just cut, copy and paste, and return a 1, and otherwise return a 0. Alright, so the way this works, let me think. Yeah. Okay. Let's cut that out. Key code and keyboard key code. Right. Okay. So this function basically says if the key code we supply is in the keyboard dictionary, and we'll cut this out and put it here. I'm trying to see if that's the best way to go about doing this. Let's do this. Let's leave it alone. We'll leave it like that. I think it can access that variable because it's a global, not global, but it's local to this function, the player function, and the key down function. Variable local localness is something that you'll learn about eventually. So I guess just to make it simpler, we're going to also supply the keyboard dictionary that we will be accessing. So we say if the keyboard key code is in the keyboard dictionary and the status of the key code is active, then we return 1. Otherwise, we return 0. So every time we run this function, it will give us a 1 or a 0 for the key code that we asked for. So we say if key code, if key down, obj kb left, and we use the keyboard dictionary, logic.endgame. Now this is something just to have a visual feedback to see if it's working. And yes, every time I press left, the game ends. Good. So now we can also do the same thing for right, but I think it'd be better if we had movement, so we'll add that in. Now the old method of doing movement that I used was basically to create a movement vector, a math utility vector, and that worked well, a math utils module vector. Now math utils is a module, Python module that comes with Blender and comes with the game engine as well, and it's used for vectors, which are basically lines that give you a velocity, a speed, and a direction, an angle. They're very useful, and I love to work with them. They make things so much simpler. Now I used to use those, like you could create your own movement vector and move things around. That worked well, but something that didn't work well was basically I was overriding the physics engine. So if I were to, for example, press right and maintain full speed and run into a box, my character would be maintaining full speed because I'm holding right and the variable's being set, despite the fact that, you probably want him to stop because, he's next to a box. Different games handle it different ways. Games like Mario, I believe, have a very constant non-physics engine approach to movement. The later games obviously do, but games like Super Mario World, for example, if you were running full speed into a wall and jumped so that you cleared the wall, you would be moving full speed as you moved right. While games like Sonic were more physics engine, I guess you could say reliant, where basically if you were moving full speed into a wall, he would stop and he would be moving very slowly, and you could see the animation, he would be like really slowly treading, and that's because he's moving slowly. He has to build up speed again. So we're going to be doing the second method of basically you needing to be able to build up speed, and if you hit a wall you'll stop, rather than the game engine kind of trying to push on despite the fact that the physics engine will say you stop. So this is a slightly different method. The simpler method with just user-defined vector is just that you create a vector up here in the init function, and then you use that as you move around. We'll be doing the physics engine version. Okay, now the player has a material. He has a sprite material, and I have the friction set to 0, and same thing on the ground, and that's because we'll be handling the friction. But the physics engine should probably handle everything else. So we'll be handling the friction so that we can slow him down if he's on the ground, not if he's in the air, different things like that. But as to everything else, the physics engine can handle that. Okay, so let's go back over here. We're going to say mv, and that's going to be our movement vector, equals obj.getLinearVelocity. And obj.setLinearVelocity, mv. So this is, we're getting the linear velocity, and then we're setting it back. That's it. There's really nothing else to it. Yeah, so one thing that you might want to, let me see if I'm doing it. Okay, I was going to mention as well. This character is dynamic. He has to be dynamic in order to move with linear velocity. So I just want to point that out. Okay, so one thing we're going to do is define some movement values that we're going to use. We're going to have an acceleration rate, which is 0.5, and we're going to have a friction rate, which is 0.1. That's probably too slow, but we'll see. And we also have a max speed rate, which is how fast he'll move when you're just mashing the movement key and have a straightaway. So we say if key down, obj kb left, mv.x minus equal obj excel. We say else if key down, obj kb right, keyboard mv.x plus equal obj excel. Excuse me. Looking at it now, it really isn't necessary to have keyboard defined here because it's a pointer probably to a global, well not probably, it's a pointer to a global keyboard thing, so we dictionary, so we don't really have to pass it around. It's not like we have to keep track of it, it's the engine's keeping track of it. So we'll just put the keyboard in the key down dictionary. I'm sorry, put the keyboard dictionary in the key down function and get rid of it from the function here. Okay, so I think that'll work. Let's see. It did it. Why not? Keyboard's not. Oh. Ha, my mistake. I have print keyboard. Here we go. Right there. Get rid of that. Alright, let me explain what I just did actually. I had print keyboard here, but keyboards have been moved down into the key down function. So keyboard has no meaning up here. So get rid of it, and that should fix it. And he does indeed move. He moves. He accelerates kind of slow. But you see that right there? How he rams into the wall and can immediately turn around? If we use the function, if we created a movement vector ourselves, that would be a, wow, that was a mistake. That would be a kind of, well not kind of, that would be bad. Because basically, by having the vector, setting it ourselves, when we hit something, he would naturally be still pushing at, positive, for example, 30 blender units a second. And when we were pressing left, he would be coming back from it. He would be going 28, 27, 26, rather than hitting something and going to immediately 0. If you wanted to have your own vector, you could use a raycast to check to see if it can move in a direction, and if not, then set the movement value to 0. But I think this would be a better method overall. Okay, so everything's working. We probably want to limit his movement of his velocity, so that he doesn't exceed a certain amount. One thing that vectors allow you to do is set their magnitude, which is how far, I guess that's the velocity, really. That's the velocity of the vector. So the vector, you can think of it like the x-axis is how fast he's moving, or the x-axis is left and right on our screen, the z-axis is up and down, and the y-axis is forward and back. But if we use magnitude, it won't work well, and that's because magnitude is for the entire vector. So you could think of it like if he's jumping and moving right, let's say at the exact same speeds, that's a 45-degree angle, and that's, let's say, a magnitude of 5. If we were to limit the magnitude to his move speed, maximum move speed, then if he's jumping, he might exceed the maximum move speed, even though we're just talking about the x-axis. So in other words, it wouldn't work well for our purpose here. The magnitude is definitely useful, but just not in this particular case. So what we're going to do is a couple of things. We want to set the y-axis movement to 0 because, it's a 2D game. We don't want him to move on the y-axis in depth. We probably also want to just hand this and say, set his world position on the y-axis to be 0. So we make sure that he'll never pop out like he did earlier when I said, whoops. Yeah, so this is just making sure that he doesn't pop out, that he doesn't go forward or back. If you want to program that in, you can, and make kind of like a 2.5D platformer, but just for this purpose, we're not going to have that. Alright, so let's limit the move speed. So, move mv.x equals obj max speed if mv.x is greater than obj max speed, else obj mv.x. Let's read this out. We set the x value of his move speed to be the maximum speed he should be able to move, like his max speed, his maximum speed, that's what it is, 5.0. If it exceeds that, so if he's moving faster on the right, to the right than maximum speed, set it back. Otherwise, leave it alone. Set mv.x to be mv.x. We'll have another one for setting it to be negative obj max speed if mv.x is less than negative obj max speed, else mv.x. So this is the same, it's just for the left as well. If his x-axis movement is less than negative max speed, then set it to be negative max speed. So if he's heading left further than the max speed should be, then set it to negative max speed. Otherwise, leave it alone. And we'll see if this works. 5 in that direction, 5 in that direction. And when he hits something, he immediately stops and turns around. Basically, he can immediately turn around. Okay, so you might be saying, well, that's a little complex. It is. I would rather use mv.magnitude, but like I mentioned, it's not best for x and z, because z takes into account his movement vector here with the z-axis. It's the vertical movement, and we can't limit that because then he would limit how fast he can fall or jump. So we want to leave it like this and manually limit his x-axis movement. Okay, good. Now, left and right. Okay, limited. Okay. Let me see. Is there anything else I wanted to do as far as movement? Oh yeah, friction. Almost forgot. That's why we turned off friction, is because we'll be handling it. Okay, so we say if. Well, no, wait, no. Let me think. Now, you might remember, if you've been reading my tutorials, that I used to do something around the lines of, if you're pressing left, move left. If you're not, but are pressing right, move right. Otherwise, subtract a certain amount by the movement speed, mv.x. So I would say like mv.x times equals 0.9. That was fine, but it doesn't add friction if you're pressing in the opposite direction. As an example, in a Sonic game, if you're running right and you press left, you'll want to basically slow down a lot faster than if you just let go of the control stick of the D-pad. And my method didn't account for that. You would be moving right, and pressing left would be slower than letting go. When really, if you're pressing left, it should add friction and pressing left. That both move speeds. That basically you're pushing to the left as well as slowing down on your own. This basically solves that by constantly adding friction, a constant as well, not a percentage. A percentage would make it so that it slows down. The character would slow down an equal amount every time. So if you're moving 1 blender unit a second, in 10 game steps, he'll be, well, each game step he'll be moving 0.9, 0.1, 10% slower. And if you're moving 100 blender units a second, same thing. Each frame he'll be moving 10% slower. So you don't want that. If you're running really fast, you'll take longer to slow down than if you're running really slowly, or walking, or crawling, or anything like that. Alright, so friction here is 0.1. Let's increase it to, say, 0.5. And this might give an error. Let's see if it does. Yeah. Problem is that movement speed here, acceleration, is 0.5, and friction is also 0.5. So no, he can't actually accelerate. So to solve this, we're going to add friction onto this. Both max speed and acceleration, because remember, friction is being added every frame. Still didn't work. Why not? Yeah. Okay, I'm gonna take the cheap way out and show you the other method of doing this with a vector. So at least I can show you how vectors work. Okay, so we're going to create a new vector. So we'll call this MVF for movement velocity, movement vector friction, mathutils.vector. It will be blank. I guess I can pass the MV, the original vector, the original movement vector. So we're going to import mathutils, which comes with Blender and the Blender game engine, and we'll see if this works really quickly. Okay, so there's no errors. No. Alright, so we have the friction version, and the friction version, yep, it has our movement speed, it has our z-axis, everything. Okay, now we don't need a lot of this. We don't need I'm going to do this little trick. We don't need Y and we don't need Z. So that's something that you can do with Python, is set multiple variables to multiple values in one line. So now we should basically have X and then 0, 0. And we do. Okay, so we are basically canceling, negating the Y and Z axis movement because we're going to be using magnitude directly. So we say mvf dot magnitude equals, or I guess minus equal, obj friction if mvf dot magnitude minus obj friction is greater than 0, else mvf dot friction magnitude. So this is pretty much what we had before. It's just in one line. We subtract friction from the magnitude, the distance, the speed of the movement vector, which is just the x-axis, if the magnitude is minus friction is greater than 0. Otherwise, we subtract the magnitude from itself, setting it to 0. And the interesting thing about vectors and magnitude is that the magnitude is the distance from the center point to the endpoint defined by the vector. In other words, magnitude is always positive, and it's basically the speed you're moving. So if I set magnitude to 0, that's setting his x-axis movement to 0. So all we have to do now is say mv.x equals mvf.x, and that should be friction and everything happily controlled in a neat little bundle. Yeah, and I bet this still doesn't work. Oh, it does. Okay. So there must have been something wrong with my code. Hooray! Hooray for not a mathematical fail, but just a human failure. Okay, so we'll just group these together a little bit so we don't have to look at something that's a little annoying. Okay, so that's working. We have friction, we have movement, everything's going well. Now the last thing we're probably going to do is add animation. So we have standing, we have walking. So what we're going to do, push this down here, is we'll say obj anim equals stand, and we'll see if that works, how the animation looks. Yep, that's the animation. Okay, so the animation for his standing should be something along the lines of 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 2, 3. Yeah, that's something else. Hold on. If you have a list like this, you can go like that, and it'll you can create a return, a carriage return, you know, push it to the next line, and it'll hold. It won't create a syntax error. If you do that in any other thing like that, it will be a syntax error. You have to use a special Python character, which I believe is that, to tell Python, hey, I'm doing this on the next line. And yep, there's no syntax error. So anyway, let's go back to what we were doing. So this is just to allow us to see the whole thing on one line. So basically, you might be saying, well, you don't need all those zeros, but basically we kind of do, because these are frames where his eyes are completely open. This is a blinking frame. This is back to his frames where his eyes are completely open. This is where he looks up. 3, 3, 3, 3, 3, 3, and then back down to normal. So we'll see if this works. Blink, look up, look down, and back. Yeah, that's it. Now we want this to run a little faster, so we'll say this is 12 and see how that looks. Pretty good. It's a little far away. Let's zoom the camera in a little bit so we can see it. Now something you might be wondering is, why is he playing this little window called game? And that's because when you have a camera under the render settings with Blender Game active, you have basically you have the embedded player, which is how large the resolution of your game is. Depending on the values you set, the aspect ratio can change and vary wildly. So you probably want a normal size, screen size like 800 by 600, 640 by 480, maybe 1360 by 768 or something weird. But usually, you know, just a 4:3 setup will be fine. And so game basically allows me to make sure that the whole screen is visible, so that I'm not missing anything. This is particularly useful if you have GUI somewhere in the corners or anything like that. You want to make sure that you basically can see everything that the camera would be able to see when your game's finished and exported in a standalone executable. Right, now, so we have him standing, looking, animating, good. Next step, we want him to walk. So what we're going to do, I'm just moving things around. What we're going to do is say if, let's create a new variable here, obj.getVelocity. If mv.x, and this is the absolute value, so basically if he's moving, so if his absolute value of x is greater than 0.1, then he's probably moving. Obj anim equals walk. Else, obj anim equals stand. Hooray! Oops. And we'll delete that one there. So this should allow us that if he's moving, he'll walk. If he's not, he'll stand. He'll look around. If he's moving, he'll walk. If he's not, he'll stand. And the final thing that we're going to do is make it so that he'll turn around, because currently he's stuck in one direction. So we say if mv.x is greater than 0.1, we'll create something so that we can tell which way he's facing. Let's create a variable. Obj facing equals 1. That's right is 1, left is -1. So we say if mv.x is greater than 0.1, obj facing equals 1. Else if mv.x is less than -0.1, obj facing equals -1. And we'll flip his sprite depending on whether he's facing left or right. So we say obj, we're going to create, I'm going to go into a little tangent here. There's different ways to do this. One might be to use the directly use the orientation matrix. You might create the orientation matrix. You might use the orientation matrix. You might use different things. I can't think of anything else that would really fit for what we're doing. But you might use a obj.apply rotation. That could work. But what we're going to be doing today is using a Euler. And a Euler is kind of like Blender's built-in rotation system, where basically you have 3 axes to rotate on, x, y, and z, or I guess x, y, and z. And so you can basically specify which direction you want to rotate things exactly. So our our object here is rotated 90 degrees on the x-axis. So we're going to create a new Euler. That's going to be obj sprite dot orientation dot to Euler. So we're making a Euler variable out of his orientation matrix. I guess it should be world orientation dot to Euler, and then we'll set it back. World orientation equals E. And so nothing should basically happen here. Yeah, it's fine. He's the same. And yeah, it's fine. Okay. Now step 2. Step 2. We want to rotate him depending on his facing. So we say if obj facing is equal to 1, or if obj facing, if you want to be quick, E dot, hold on. Yeah, Z equals math.pi. Now you might be wondering what is this? But you probably know by now that Blender rotates with radians, and a radian is, I don't know, a different method of rotation than degrees. 180 degrees is pi. A full rotation is 2 pi. So half of pi is 90 degrees. Pi is 180 degrees, you know, and 2 pi is a full rotation. So if he's facing right, we want to set the z-axis of his rotation actually to 0. And if he's facing left, we'll just say else. We want to set his rotation to be math.pi, which is 180 degrees. And so that doesn't work. Why? Why doesn't it work? Hold on. You know what? I think I might know what's going on here. My mistake. I said if you want to be quick, idiot. But actually, OBJ facing, it's always positive. It's always becomes true, basically. This is saying if the variable is true, evaluate this line. If it's not true, evaluate this line. The problem with that is that anything other than 0 is true, and 0 is false. So I need to make sure that it's equals 1. And we don't have to do this, but just to make sure I'm not being an idiot, if it's equal to -1, flip it. So if he's facing right, or 1, make his rotation 0. If he's facing left, or -1, make his rotation math.pi, rotating him on the z-axis. So he faces the other direction. And there he is, folks, in all of his red, shuffly, laggy a little bit, 800 by 600 glory. That's it. That's a game. That's a little game right there. Well, that's, yeah, everything's going well. Logic's not too high. Yeah. So that's it for this little tutorial. I probably won't upload the example files unless people want to have them. If so, then I'll make a little. I guess I'll put them up. I'll put up the example files, and yeah, you can play around with it. This has been a quick little tutorial. Well, actually, it's been like 50 minutes, but this has been a tutorial on how to do a 2D game in the Blender game engine, implementing some logic, some gameplay. Someone asked for a tutorial on implementing more ideas and how to do that in a game standpoint. I probably will do that next, and it shouldn't be too hard. I think that it'd be interesting to actually implement something into this game and add something. So yeah, thank you very much for watching. I've been SolarLune. If you want to donate to help fund more tutorials like this, help me to make more things, and to say, please make more stuff, or if you have any suggestions about tutorials to make, please feel free to make them, and I'll see if I can get on them. Alright, yeah, have fun with Blender and GIMP and making stuff, all with free software, basically. By the way, this was recorded on Cam Studio, which is also free software. Alright, have fun.